Hello, pre-calc honor students. Here we are, the last topic in this chapter 12.9, determinants and vectors in three dimensions. And we're going to define and apply the cross product, which is mainly come up with so that you could have a vector perpendicular to the plane of another two vectors. That's eventually going to help us write equations of planes. First, we have to talk about this concept of unit vectors in each of the three directions, the I, j, and k vector. And here they are in the plane. It's called a unit vector because it's one long, and it's in the directions of our three axes in 3 space. Now, write 3, 5, 6 in terms of unit vectors and graph it. Well, 3, 5, 6 is 3, 0, 0 plus 0, 5, 0 plus 0, 0, 6. And so that's 3 times 1, 0, 0 plus 5 times 0, 1, 0 plus 6 times 0, 0, 1, or 3i plus 5j plus 6k. And we can simulate this on our graph paper by just cloning these puppies. Let's clone this. We have 3 of these, 3 times. Clone it again. 2, 3, 4. Let's clone one more. Take this one up. 3, 4, 5, 6, 6, there we go, and start stacking these up. So there you go, there's your 0.356 as a sum and scalar product of these unit vectors. Okay, now these are going to help us do the cross product. Because to do the cross product between two vectors, we just put a row of unit vectors along the top row of the determinant, then the first vector, ABC, and then the second vector, DEF. And the result that we're going to get from this is a whole other vector, perpendicular to the plane of the first two. So to find the cross product of 2, 3, 4, and 1, 0, 5, we can go like this. We're going to expand it by minors. Well, first of all, I'm going to write it in here. So that's I, J, K is your top row, and then A in this case is going to be 2, 3, 4, and the second vector is 1, 0, 5. So we have I times the minor of I, which is 3, 4, 0, 5, plus J times the minor of J, which is 2, 4, 1, 5, K times the minor of K, which is 2, 3, 1, 0. Oops, I think we're forgetting something. It's a little negative sign here. Remember, because we're doing a determinant, and the J is in a negative position there. Got to put a minus there. So, let's see what we get for these vectors then. This is I times 15 minus 0 plus negative J times 10 minus 4 plus K times 0 minus 3. So we get 15 I's. Let's see, negative 6 J's and negative 3 K's, minus 3K. So that's just basically the vector then, 15, negative 6, negative 3. 15, negative 6, negative 3. Now, we'll use this again in a second, but here's some of the other properties of the cross product. U cross V is perpendicular to U and V. That's the whole point. You're creating a vector perpendicular to the plane of the first two. Also, V cross U is the opposite of U cross V. You end up with vectors in opposite directions. And U cross V. So in other words, here's V, U cross V. There's a vector going up like this. And here's U, V cross U going in the opposite direction. that. Same magnitude, but just exactly the opposite direction. So, so here's a little something called the right-hand rule I dug up from the internet, and it's basically can help you decide the direction of the cross product, because the order in which you put the two vectors makes a big difference here. So this up here is u cross v. Okay? Now if you line up your fingers and put your first finger in the u direction here, here's u, and your second finger in the v direction, your thumb will point in the direction of u cross v. Notice v cross u is down here in the opposite direction. So if you put your first finger in the v direction and the second finger in the u direction, your thumb will point downward, and that's how you can use your right hand to figure out what direction these are going in. We also see that the magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of the angle between them. And theta is this angle in here like this. Here's theta, the angle between two vectors. Now we already had a way to come up with the angle between two vectors in 3 space. But this is a way to come up with the area of the parallelogram of something in 3 space. Because remember before, when we took the 3 vectors and did their determinant, that gives the volume of the parallelepiped. Now here's a way you can do a area of 2 vectors in 3 space. Okay, now there's a couple other properties I want to talk about. U cross V plus W, well, what do you think? Yep, it distributes U cross V plus U cross W. And U is parallel to V if and only if the cross product, the magnitude of the cross product, or just the cross product itself, is equal to 0. Because basically, remember, if the cross product equals 0, then the sine of theta will equal 0. And that happens at 0 degrees or 180, and that puts those two vectors parallel to each other. Okay, and now we're just going to do one big example of how we apply all this. Find a non-zero vector perpendicular to the plane containing the points 1, 0, 3, 2, 5, 0, and 3, 1, 4. What we're going to need first is to come up with a cross product. The non-zero vector, we have to get 2 vectors in the plane. So let's look at vector PQ and look at vector PR. Now PQ goes from 1 to 2. So that's a 1, 0 to 5 is up 5, 3 to 0 is actually down 3. P to R, we go from 1 to 3, so that's up 2, 0 to 1, so that's up 1, 3 to 4, so that's up 1. So there's PR and PQ. Now we just need the cross product. PQ crossed with PR will give us a vector perpendicular to the plane of the first 2. So I, J, K, and then put down 1, 5, negative 3, 2, 1, 1. In this particular case, because we're just looking for a vector perpendicular to the plane, it doesn't matter if we end up getting something in the opposite direction. It'll still be perpendicular to the plane we're looking for. So we get I times the minor of I, which is 5, negative 3, 1, 1, minus J times the minor of J, which is 1, negative 3, 2, 1, plus K times the minor of K, which is 1, 5, 2, 1. So we get for I, 5 minus a minus 3, minus J times 1 minus a minus 6, plus K times 1 minus 10. So that's 8 I's, let's see, 7 minus 7 J's plus negative 9 K's, or just the vector 8, negative 7, negative 9. 8, negative 7, negative 9. That helps us out a lot here now, because now we can go to the next phase, find the equation of the plane containing the points. We can use this normal vector to the plane, which is 8, negative 7, negative 9. And this becomes the coefficients of x, y, and z. 8x minus 7y minus 9z equals some constant d. To find that constant d, we can put any of our original points in. So let's put in let's put in p, which is 103. So 8 times 1 minus 7 times 0 minus 9 times 3. So that's 8 minus 0 minus 27. And I believe we get a negative 19 for d. And now you can put it all together then. So the equation of the plane that goes through those 3 points is 8x minus 7y minus 9z equals negative 19. There you go. And then you can go back and see, make sure that all the points work. We already checked 10325. Does Q work? 250. You get 16 minus 35, 19. Does R work? 314. We get 24 minus 7 minus 36. That checks out too. Okay. So there's your equation of the plane. Now, our last application in this section, then find the area of the parallelogram with sides formed by PQ and R. We can just look at the magnitude of the cross product of PQ and PR. So that's the magnitude of our vector 8, negative 7, negative 9. So that's the square root of 8 squared plus negative 7 squared plus negative 9 squared is the square root of 194, or about 13.9. Now, recall from geometry there are many ways to determine a plane. You could have 3 non-collinear points, and we just did an exercise in doing that, where we took 3 points and we formed 2 vectors and created the normal. What about 2 unique parallel lines? How would you come up with the equation of a plane if you're given that? 2 parallel lines like this in space. Well, I'm thinking you come up with this vector coming this way. You got a couple points on either line and make this vector like this, and now you can do the cross product of these 2 vectors. Just some hints here. 2 intersecting lines. Well, you can take the direction vectors of each line and do the cross product of those. And then you're still going to need 8 points somewhere on either of those 2 lines. A line and a point not on that line. That could be tricky. Well, you got the direction vector of this line, and you can take any point on the line and draw the direction of the vector to the point not on the line. And now you can take the cross product of those 2. And lastly, a set of points equidistant between 2 endpoints of a segment. That's where the distance formula can come into play. You want to get this plane, and here are these 2 points, and remember we looked at this before? And you can create the equation of the plane that way. All right, flange out.